Okay, we are continuing to talk about titrations here. So last time we talked about titration of a weak acid with a strong base, and then we got into this titration here, which is a titration of a weak base with a strong acid. So again, in this orientation, it's a little bit different than the ones we talked about before. We actually have the acid up there in the burette, and in the bottom there, we actually have our weak base. So in this case, we're actually adding acid to base. And this is why the titration curve here looks kind of upside down. And that is because we're actually starting with a base. And that means we have a basic pH. As we continue to add our acid, we do start to drop pH. We also see a similar vertical sort of drop down to the equivalence point here. And then we're kind of flattening out at the end. So last time we talked about a couple of spots on here, and it's really the same 4 spots that we talked about in the previous ones. Really, before we begin to the equivalence point, at the equivalence point, and then finally past the equivalence point as well. So we got to the first couple last time. So a reminder that really when we start here, or before we start, really, I guess is a better way to know that, before we start, before any HCl is added. Really, again, the only thing that we have in here is a weak base. So we would want to calculate the pH by doing a weak base problem, which in this specific example would be the ammonia plus some water, giving you a little ammonium hydroxide. And again, as we talked about last time, you can, put them together or keep them apart. But we can do this guy in molarity as we haven't added any volume yet. We can have zeros here, minus X, plus X, plus X. And at equilibrium, we get these guys. Here, obviously, we would solve for X. And we also want to remember, since this is a base, that X is not going to be our H+, but it will be our hydroxide concentration. And that means we first need to calculate the POH and then get ourselves to the pH. So this is very similar to what we see in the weak acid strong base titration, except that we're starting with a weak acid. So you have to do a weak acid problem. Here you're starting with a weak base, so you need to do a weak base type problem. Any questions on that there? I think we also talked about the second point here, but just to review, once we start the titration and we sort of hit that second spot there, we actually do have a reaction that is taking place. And what would happen is, there you go, maybe. That would be here. Once we start our titration, we will get the reaction between the ammonia and the HCl. Here, because we are before the equivalence point, we are starting with the weak base. We're adding the HCl. So as we talked about previously, I just made up that number like we did before. We would definitely have less moles of our HCl. That would make our HCl really the limiting reagent here. It's going to get used up. And what we are left with at the end is really NH4 plus and NH3. There is some chloride there, but again, if you kept the NH4Cl together, it would all be together, so you could break it up. If you did break it apart into Cl minus, that's why it's scratched out here, because Cl minus, again, is still a neutral salt, so it wouldn't affect the pH. But what we really have here, and what you'll always get in this type of titration at this point, is a buffer. So again, it's very similar to the previous type of titration we talked about with the weak acid and the strong base. The difference is here you will end up with a buffer that is, for the most part, basic. So you'll end up with a basic buffer. Again, it can turn acidic closer to the equivalence point, but a majority of it will be pretty much a basic sort of pH buffer. So a couple of things you do want to watch out for. You basically do need to do an ice table like last time. You want to convert back to molarity using the total volume. And again, you do have 2 options as to how you could get to the pH. probably the easiest route would be to use the Henderson-Hasselbalch equation and go into it after the ice table. A couple of things you want to watch out for, as we talked about at the end last time. You do want to definitely always make sure base goes up on top and the acid goes on the bottom. And more importantly, especially in this type of titration, you want to make sure that you do have the pKa value. Again, you would probably be given the Kb value, so you don't want to obviously use that here. Alternative to that, you could use that POH version of this equation with the pKb if you want. So that's another option. That's why we wrote down here last time. Again, just remember that's sort of an important little relationship there. And since you probably will or would be given just the Kb value, you could convert it to the pKb, basically subtract 14, and you could get the pK value pretty quickly that way. So you could go into the Henderson-Hasselbalch equation and get your pKa value. The other option, obviously, is you could take the Kb and divide it by, or take Kw and divide it by the Kb to convert it into the Ka, and then obviously get the pKa value from that as well. So a few different ways you could get it, but that's probably the best route, is to make sure you have it and go into the Henderson-Hasselbalch equation. Alternative to that, like normal, if you choose not to use it, you can obviously just do an ice table, a second ice table at this point. And you actually have two versions of that. You could either do it the basic ice table with the Kb value and then get it from the POH to the pH, or you could use NH4 plus as your acid and do a Ka type of calculation. So, there are a few variations of ways you could get to the answer. Choose whichever way seems the best for you would be good. Any questions on before the equivalence point here? Okay, then we will pick up there, which if we're looking at our graph, will take us actually to the equivalence point. And much like what we saw before, as we approach the equivalence point, we basically have this buffer happening here. So we're kind of breaking through the buffer as we get closer to that equivalence point. And again, that's why we kind of see that big drop to the equivalence point. And then obviously afterwards, we're just dumping a lot of acid in. So we see that big jump after the equivalence point. And again, we get that kind of vertical drop in this case to the equivalence point. So let's see what happens at the equivalence point here. We have our reaction, which is our HCl plus our NH3 in this case, going to give us NH4 plus. And again, I'll separate them, but you absolutely could keep them together as, again, NH4Cl if you wanted to in this case. We will initially start with our moles of our base. And again, I'm going to use the same made up number that I've been using, which is we're starting with 4. And obviously we are adding our HCl. So as we talked about a number of times, we should know that when we reach the equivalence point, the moles of the HCl in this case should be the same. So that's what you see what it means. We would have 0 of that guy. Change here would be -4 plus a 4. That means at equilibrium, nothing, nada, and 4 moles here. Like normal, we're going to convert this guy back into molarity by dividing by the total volume. Once again, here I recognize Cl minus is a neutral salt, so I'm not really going to put any numbers there just in case, so I don't try to use them incorrectly here. Any questions on the ice table? Now, at this point, we could definitely use our ice table here to help us see what's going on, and we can see that we really have only NH4 plus basically there. So what we always have to decide is, since this is pretty much a salt here, we needed to decide, will anything go through hydrolysis? I just eliminated Cl minus as it obviously came from HCl. How about the NH4 plus? Will that go through hydrolysis? NH4 plus comes from NH3. NH3 is a weak or strong base. It is weak, which means NH4 plus is relatively strong, and it's going to act like an acid and should go through hydrolysis. So we will get a secondary reaction that's occurring here, which is the NH4 plus will react with the water. And again, knowing that this guy is a base means this guy is an acid. Definition of an acid is it's going to donate the H plus over. When it donates H plus over, we will get where it came from, and we will produce H3O plus here. Any questions on that reaction? This solution should be acidic, basic, or neutral at this point. It should be acidic, right? We are creating H3O plus. And that means that initially it would be this concentration from above. So above is what we would use there. These would be zeros. And again, this would be some X's here. This would go into our K what? K, A, B, C, D, E, F, G. Nobody said G, so that's good. All right. It is a Ka. Again, we see the H3O plus here. So this is a Ka value. And that would obviously be our products over our reactants. That once again is important because you are probably not given the Ka value in this problem. Again, you are probably given the Kb value. So that is your Kw thing that you need to do. Once you get everybody there, we will solve for X. In this case, X actually does equal the H plus concentration. That means we could go into the pH formula to get us to the pH. So just like sort of the previous titration, when you reach the equivalence point, you will need two ice tables. The first table is really to figure out the concentration of the salt. Second ice table is a hydrolysis problem, and you will always end up in an acidic situation in this case because you will have a salt that came from a weak base, which means it will act as an acid and donate the H plus over to water and produce H3O plus in this particular case. Any questions on any part of that calculation there? All right, so we reached the equivalence point, and clearly if we were stopping our titration in a normal titration, we would stop there. But we will continue on in our titration here to pass the equivalence point. So really past the equivalence point, what we're going to see again is that drop in the pH like we see on this graph here. Again, because we're equal at that point, and now we're just adding acids. So we're going to see that good drop in pH that's going to occur. So what we end up with here at that fourth part of the titration curve is after the equivalence point. And again, we will still have our reaction here. And once again, using some made up numbers here, starting with our 4 moles of the NH3. Because we are past the equivalence point, we should have more moles of HCl. And we'll just make up 6 as a nice number. This would be 0. This is going to cause the same sort of reverse situation that we talked about earlier, where our moles of NH3 now are the limiting, so we don't get a negative number. Gives us 2 moles, 0, and 4 moles of this guy. At this point, we can convert these guys back into molarity, dividing by the total volume. This gives us 2 things left over at this point. Again, I'm ignoring the chloride as it is a neutral salt. We have this guy here and this guy here. Are those guys a buffer? They are not a buffer. So we do have 2 things. We have our salt here, which again, as we determined a second ago, will go through hydrolysis, acting as an acid. We obviously have this guy here, which is HCl, which is a strong acid. So again, at this point, what we will do is usually ignore the contribution of the salt, because in comparison of the salt being an acid to HCl, which is a strong acid, HCl again is a much stronger acid. As we talked about maybe last time, it just needs to go for a swim and you have produced H plus. The NH4 plus got to go find some water, do a little reaction, and it's still a weak acid type reaction as well. So what that means is we essentially will have at this point the H plus concentration, and that would allow us to directly go into our pH. So you do need to do one ice table past the equivalence point here. Purpose of that ice table is to figure out how much of your strong acid you got left over. And then you could go right into the pH equation at this point. So the 4 parts on this type of titration is very, very similar to what we see with a weak acid and strong base. Again, obviously one is just increasing the pH and the other one is dropping in pH as you're adding acid. Any question on any of those parts? Question on how to calculate pH at any of these places? All right, well then that brings us to the part of the program where I take a nap and you work on all these parts, and I'll wake up in 30 minutes and then we'll go through these to make sure everybody understands this. Work on all these parts. This is a titration of HNO2 with sodium hydroxide, Ka value down here for HNO2. We want to know the pH initial solution. So before we start the titration, we want to know the pH after you add 80 milliliters of sodium hydroxide to it. We want to know what is the pH at the equivalence point, and finally, what is the pH after you add 105 milliliters of it. Feel free to work together and all that. So we're going to work on it about 20, 30 minutes, and then we will go through it and make sure everybody is hopefully on the same page. Yeah. So let's take a look. Hopefully you made some dents into this here. So let's see how you're doing. And let's go through it here. So first off, when we look at this, this is obviously a titration occurring. So we definitely want to sort of maybe identify what type of titration we're dealing with here. So obviously I see a Ka value. So I know this guy is a weak acid. And obviously sodium hydroxide here is a strong base. So again, here we're doing a titration of a weak acid with a strong base. Setup is like we talked about, sodium hydroxide would be up there in the burette and our acetic acid there, not acetic acid, our HNO2 would be on the bottom. And we're adding our sodium hydroxide to it, which means we should have a titration curve that sort of looks like this here. So initially here, before we begin, we haven't added any sodium hydroxide. So really the only thing that we got going on there in the beaker is a weak acid. So that is what we should start with. So we'll do that. Let's start with A here. So A would be really just the HNO2, which has a Ka value of 4.5 times 10 to the minus 4. So since we have not added any sodium hydroxide at this point or anything like that, it is just a straight Ka problem. And we can use molarity here because we haven't added any volume. So I'm just going to do the weak acid that's going to dissociate into H plus and NO2 minus. So initially we'll use our concentration, which was 0.1 molar. This guy is going to be 0 and 0. Change will be minus X plus X plus X to our equilibrium of 0.1 minus X, X, and X. Any questions on the table there so far? This will obviously go into our Ka expression here, which would be our products over our reactants. And in this case would give us X squared 0.1 minus X is equal to our Ka value of 4.5 times 10 to the minus 4. It is a small value, so you could assume that X is equal to 0. And if you did, you hopefully should have checked it. And if you checked it, you hopefully should have got an unhappy face because it was like 6.7%, which means it was like a little too high for our capabilities here. So we do need to go back in this case, and a good reminder that you should always check it because it will not always work. We do need to go back and solve it using our quadratic. So we're basically going to take our bottom here and multiply it to the other side. And if you do that, you get x squared is equal to 0.000, one more 0.45 minus 4.5 times 10 to the minus 4x. Kind of combining everybody to the same side gets us x squared plus 4.5 times 10 to the minus 4x minus 0.000045 equals 0. That goes into our x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Putting our values in gives us an x is equal to minus 4.5 times 10 to the minus 4. Plus or minus, if you did the square root, kind of got all the numbers in there, 0.000182, which then if you square rooted it, should have got you to like 0.0134 in that ballpark. Divided by 2 times 1, which would be 2. Gives us 2 x values. We get an x value that is 0.006485. And a negative number that I did not calculate because I can't have a negative number, so I just ignored it. That means that this guy here should be our H plus concentration. And put a little molar on it. That means we can then go into our pH, and it looks like on our opening titration here, we're going to open up with a pH of about 2.19 there. Any questions on any part of that calculation? Now, in this particular example, if you did the assumption, you got a pretty close pH, but it technically would be wrong because you shouldn't have done the assumption. Yes. And it won't always be the case that they'll be close, but sometimes they are. And it's really because it is only really 6.7% hydrolyzed, ionized instead of 5%. So they're very close. So that's why you get a close answer. Any questions on any of our so that step there? We got that number, yes, before I put it up. Yeah, so it's a better question to ask. It's like before I put it up there. Maybe the better question is after I put it up there, did you get it? That's it, I suppose, as well. All right, let's do part B there. So at part B, we're going to actually add our 80 milliliters of base to this. So we are going to obviously get a reaction. We're also starting our titration here. So in B, we are adding 80 milliliters of our sodium hydroxide here. So we definitely need to do an ice table. We definitely need to do it in moles. So we might want to get our moles of everybody. And our reaction here is going to be our HNO2 plus our sodium hydroxide, a little double displacement action happening here, giving us a little NaNO2 plus a little H2O. So remember, because we are adding here, we want to make sure that we do it in moles. And we are starting with, again, 100 milliliters of 0.1 molar HNO2. So that is 0.1 times 0.1. When you convert the milliliters into liters, gives you 0.01 moles of our HNO2. For our sodium hydroxide, we are adding 80 milliliters, so that's 0.08 times the molarity of our sodium hydroxide, which is also 0.1, gives us 0.008 moles, and that would be 0 there. Any questions on the moles there? So if we're not sure where we're at, we could again use our ice table to help us decide that. Am I before, at, or after the equivalent point in this case? And before, and even though the question says equivalence point next, that helps you as well. But a reminder that we are starting with this, we are adding this guy, and we have less moles of what we're adding. So that means we are before the equivalence point. So again, your ice table can help you determine that. That also means that we know then that the sodium hydroxide here should be our limiting. So our change would be our 0.008, our 0.008, and a little plus 0.008 here. Going to get us at equilibrium here. 0.01 minus 0.008. 0.002 moles. This guy zeroes out, and 0.008 moles here. At this point, as we've talked about before, we definitely want to convert back into molarity by using our total volume, which in this case is we started with 100, we added 80, which means really our total volume here is 180 milliliters at this point. So we want to take these guys and divide it by 0.18 liters, which is converting that into liters. And that gets us here 0.002 divided by 0.18, 0.0111, and 0.008 divided by 0.180. A lot of repeating numbers, 0.444 molar here. First off, any questions on the ice table at this part? So again, if you get to this point, you successfully completed the ice table and you still are of lost of what is going on, you can use your ice table again to help you understand what's happening. I have this guy and I have this guy that is left over. Those two guys, are they related to each other? They are a buffer, which, by the way, just knowing that we are before the equivalence point in this type of titration, even before we did the calculation, we should expect it to end up in a buffer situation. So as we talked about before, if you kind of figure out where you are in the titration curve, even before you do the calculation, you should really know where it should end up at. And that obviously helps you focus on what you should get to. That again means since it really is a buffer here, we can go into the Henderson-Hotspot equation right off the bat. And that means that our pH would equal our pKa value plus the log of the base over the acid. Obviously here our pKa would be minus the log of the Ka, which was our 4.5 times 10 to the minus 4. And that gets us minus the log there, 4.5 to the minus 4. Looks like a 335. So our pH would be 3.35 plus the log. We want to make sure we get the correct one, which is the base, which is this guy is the base. So that's going to be our 0.0444 divided by our 0.0111. And .395 looks like a pH that we are at this point in the titration. Any questions on any part of that step? Again, like normal, if you wanted to, you could double ice table instead of the Henderson-Hotspot. And that would be obviously just like the first table in A with the concentrations on both sides. Also, it does make sense as we're doing a titration and we are adding sodium hydroxide, we do see the pH go up, right? So we started at like 2.19 and we've added some HCl and we're moving at least in the correct direction. Clearly, if you did this part and you went below your first pH, then you were definitely going the wrong way. Any questions on that there? All right, then that takes us to the equivalence point, which is part C here. So once again, we are adding 0.1 molar sodium hydroxide to 100 milliliters of 0.1 molar HNO2. So we are going to get our reaction here, which would be HNO2 plus our sodium hydroxide, giving our NaNO2 and our H2O here. Starting with our initial moles of our HNO2, we should have the same amount we started with, obviously, here, which is 0.01. Now, because you know you're at the equivalence point, there's a couple of things that you might need to figure out, which is the volume to reach there. What is the volume to reach the equivalence point here? The answer is 100 milliliters of sodium hydroxide is needed to do that. I know that because, well, the quick way is the concentration is the same and it's a one-to-one. You need the same amount. You could also do M1V1 equals M2V2 because it's a one-to-one. 100 times 0.1 divided by 0.1 gives you 100. Lastly, if you were not sure, the one thing that you should know if you got into your ice table is the moles of sodium hydroxide at this point should be the exact same number, which means even without that, this guy should be the same number, which means now you have the molarity and you have the moles. So you could do that the liters is equal to moles divided by molarity and figure out the volume as well. So 3 different ways you could figure out. 4th way is a true stoichiometry problem to figure out how much volume you get there. You may be saying, if I know the moles, is it important to know the volume? And it is, because you need to convert back to molarity here after this table. So you do need that volume to get to the correct molarity at the end of this. Any questions on that there? All right, so obviously once you get to this point, however you get to this point, it's got to be that number since it's the only number there, right? So, and that's what we would expect at the equivalence point. Since we have equal moles of those two, we would have plus 0.01 moles here. Nothing and nothing of these two guys, which is exactly what should be happening here. 0.01 moles. At this point, we could convert back to liters, which is why figuring out that number is important so that you could add it to that number. And we see that our total volume at this point is 200 milliliters to reach the equivalence point. That's quite the titration. All right, so that is 200 milliliters, which is our total volume. That means we want to divide here by 0.2 liters. Gets us 0.05 molar here. Any questions on that table? Looking at this ice table, we pretty much got one thing left there, and it is this guy, which is a salt. So always when we have a salt, we want to think about hydrolysis, and will it go through it? And the question is, will it go through it? Will this salt go through hydrolysis? The answer is yes, it will. There's 2 parts to the salt. Will the sodium part go through hydrolysis? It will not. It is the NO2 minus part, which comes from the weak acid, right? And that's how we know it goes through hydrolysis, because that NO2 minus comes from this guy, which is a weak acid, which means the second thing that's going to happen is this NO2 minus is going to react with water. Again, if you're not sure how it's going to react, because it comes from a weak acid, the NO2 minus is pretty much going to act like a base, which means it's going to accept the H plus. Plus, logic tells us the NO2 minus doesn't have an H to give, so it makes it kind of hard for it to do that. So it can only accept the H plus. Don't overlook logic. And HNO2 is formed, which again, you always form where it came from. Plus a little hydroxide action at that point there. Now, based just on the equation here, I should expect my pH to be acidic, basic, or neutral. Should be basic here, even before I kind of finish the calculation. So let's do that calculation. We're going to carry our concentration from the first table down. 0.0500. Change will be X's here. And again, typically, if you use a molarity, probably X's, not 100% of the time, but most of the time. And if you're using moles, typically numbers is the change. This is going to go into our K, which would be our products divided by reactants. What type of K is this? This is a KB. And again, we are not given the KB value here, but we're given the KA value. So I'm just gonna back up somewhere to write that. I think we'll go this way. So here's our KA. So remember our KW equals our KA times our KB. And since we're looking for the KB here, it would be 1 times 10 to the minus 14 divided by 4.5 times 10 to the minus 4. That gives us a KB value here of like a lot of twos, 2.22. A lot of these same numbers in these problems here to the minus 11 in this case. So we definitely want to make sure that we use that. So rolling back this way here, we will go with our 2.2 times 10 to the minus 11 is equal to x squared divided by 0.05 minus x. I'm going to assume that x is equal to 0 here. So I'm going to take my KB times it by 0.05. I'm also going to do a little square root action on it. And if I do all that good stuff, again, multiply it to the other side, take the square root, I get an x that's equal to, a lot of zeros there, 0.000000105 there. Are 1.05 times 10 to the minus 6, looks like. We do want to check it, so we'll divide it by 0.05, we'll times it by 100, and I think we are pretty good there, so our assumption is good. That means that that number that we just got there, which is 1.05 to the minus 6, should equal our OH minus concentration, right? Not our H plus concentration. So we'll flip the page here to finish it. So our OH minus concentration will equal 1.05 times 10 to the minus 6. That allows us to go into our POH, which gives us, I punched that in right here on the calculator. Try that, try that, try that. Gives us like a, looks like a 598 on the POH. That means our pH here would be 14 minus 5.98. And try that again there. Pretty sure it's not 19. Let's try that, minus 5.98. How about an 802? That sounds a little bit more reasonable, I suppose. It's super basic. So 8.02 there would be our pH. It is basic and sort of what we would expect. Any questions on that there? All right, so since we're at the end, we're going to lay it up here, but I do want to